Today we are talking about section 4.2, increasing, decreasing functions using the first derivative test. So the first derivative test, is a method for determining whether a critical number is a max, a min, or neither. So if f prime of x changes sign around a critical number, then the function f of x has a local or relative extrema. Then f of x has a local or relative extrema at that point. So basically, we're analyzing the sign of the derivative. So if a function is increasing and then it changes at this maximum point and starts to decrease, the derivative of any point on this increasing function will have a positive slope. So if I have positive slope, I have my critical value, that's where the derivative is 0 or undefined, and I go to any point on the decreasing side, my slope would be negative. So if I go from increasing to decreasing, I have a max, and vice versa. If I have a function and I'm going from decreasing to increasing, that the slopes are going to be negative. Slope of 0 is where I have my critical number, and then my slopes become positive. So changing from negative to positive would mean I have a local or relative min at that critical number. So the procedure for using the first derivative test to determine increasing, decreasing, and therefore max and min values, we're going to find domain restrictions, find all the critical numbers, that's where f prime equals 0 or is undefined. We have to make sure the domain restrictions, the critical numbers aren't domain restrictions. We're going to locate the critical numbers and domain restrictions on an f prime number line and label the critical numbers, and then do a sign analysis for each interval that those critical numbers create. And then wherever we go from, wherever we have a sign change, we have either a max or a min. If they actually ask you what the max or min is, that means we need to find the y values. All right, so we have 3 examples. We're going to find the intervals on which these functions are increasing and decreasing, and then find all local extrema as points. So when they ask you for this as a point, that means that we want to find both where the max or min happens and what the actual output is. So let's go ahead and check out these examples. So example 1, f of x equals x squared minus 9 all to the 2/3. So our domain for this, we don't have any restrictions. This would be a cubed root if we wrote it as a radical, and cube roots don't have any domain restrictions, so this is all real numbers, so we don't have to really worry about that. Then we need to find our critical numbers. Our critical numbers are where the derivative is 0 or undefined. So let's go ahead and take the derivative. So here we're going to have to use our chain rule. Bring the power down, leave the inside like it is. Power minus 1 gives me a negative 1/3. Derivative of the inside is 2x. So when we simplify this, our derivative is 2 times 2x, would be 4x, over 3, and then if I bring that x squared minus 9 to the negative 1/3 down and convert it to a radical, that would be the cubed root of x squared minus 9. Now it's important to look at our derivative in this way because we need to, when finding our critical numbers, we need where it's 0 and also where it is undefined. So the zeros are just going to come from setting the numerator equal to 0 and solving for x. So x equals 0 is one of our critical numbers. And then to see where this is undefined, I'm going to focus on the denominator. So we need to remember that we can't divide by 0. So I want to see what will make this denominator equal 0. So if I divide by 3, that's just going to still be 0. Cube this to get rid of the cubed root, still 0. So I'm really solving where x squared minus 9 equals 0. So this is x equals plus or minus the square root of 9, or x equals negative 3 and 3. So we have 3 critical numbers. We didn't have any domain restrictions, so we can go ahead and use all 3. And we are going to create kind of a number line using the critical numbers and the domain restrictions from our derivative. So if I create that, this is 4f prime of x. I'm going to clear this and just let's write our derivative, just kind of give us a little bit more room here. So again, our derivative was 4x over 3 cubed root of x squared minus 9. So our number line with my critical numbers on it will be negative 3, 0, and 3. So we want to see what the sign of the derivative is on each of these intervals. So we have 1, 2, 3, 4 intervals that we need to check out. So you're just taking any value of x that's in the interval starting from negative infinity to negative 3. So an easy number to plug in would be negative 5. You just have to make sure that you don't actually use the endpoint. So if I plug negative 3 in, we'd end up dividing by 0, which wouldn't give us a sign. So when I do f prime of negative 3, we get 4 times negative 3 will give me a negative 12. And we really don't even care what the actual output is. We just care about the signs. And then in the denominator, I'll get 3 times the cubed root of negative 3, excuse me, oh, my bad. I got focused on us not using the endpoints and ended up using those. That is not good. So we actually want to use negative 5. You could use negative 5, negative 4, negative 6, negative 10, whatever is going to work best. Just anything that's between negative infinity and negative 3. So 4 times negative 5 is a negative 20. Just erase that. And then let's plug the negative 5 into the denominator. That will give me cubed root of 25, because negative 5 all squared is positive 25 minus 9. You don't even have to finish this. We can see what the sign will be. We have a negative divided by a positive. So my sign here is negative. So any number between negative infinity and negative 3, non-inclusive, will give us a negative output for the derivative. So now let's check the second interval. A number that's between negative 3 and 0. Let's try negative 1. And we're plugging this into the derivative. So 4 times negative 1 is negative 4. 3 times the cubed root of negative 1 squared is 1. 1 minus 8, 1 minus 9 is negative 8. So we have negative 4 over cubed root of negative 8 is a negative 2. So that would be negative 6. So we have a positive. So my output for any value between negative 3 and 0 will be positive. Now let's check 0 to 3. So I'm going to put 1 in. So 4 times 1 is 4. And then we have 3 times the cubed root of 1 minus 8. I keep saying the answer. 1 minus 9 is negative 8. So that's going to be a positive over a negative. So any value between 0 and 3 will give us a negative output. And then let's check the final one. And it doesn't always alternate. We're going to see an example where it won't alternate. So you do always have to check these. So when we check, let's put in 5. That would be 4 times 5 is a positive 20. So f prime of 5 gives me a positive 20 over a positive number on the bottom, because cubed root of 25 minus 9 is positive. So my output for anything between 3 and infinity will be positive. All right, so what does this all mean? So when we interpret this, this is telling us that our derivatives, the slope from negative infinity to negative 3 for the original function, the slopes are decreasing. And then at negative 3 we have a change, and we go from decreasing to increasing, and then increasing to decreasing, and decreasing to increasing. So if you have a change in the sign of the derivative at the critical number or an excluded domain value, then we say we have either a max or a min. So it just depends on what the function is actually doing. So let's list where we're increasing and decreasing. So we are increasing from negative 3 to 0, and from 3 to infinity, and decreasing from negative infinity to negative 3, and from 0 to 3. So that means that I have, if I'm going from decreasing to increasing, I'm going to have a relative min at, let's see, that will be at negative 3 something, and I have a relative max as I go from increasing to decreasing at 0 something. And then again, decreasing to increasing, we have another relative min at negative or positive 3. Now to see what that actually is, we need to plug these values into the original function. So if you're actually trying to find what that max value is or that min value is, it always goes to the original function. So if I plug negative 3 into this original, I would get negative 3 squared is 9, 9 minus 9 is 0, so I get 0, same thing for 3. And if I plug 0 in, I would get negative 9 to the 2/3, which we'll just leave it like that, negative 9 to the 2/3. Okay, so we just analyzed this function using the first derivative test. Okay, so let's move on to example 2. Example 2, we have f of x equals x to the 4th plus 3 all over 3x. So our domain, let's always start with your domain restrictions. Our domain restriction is that x can't be 0, as we have a denominator, and we can't divide by 0. Next, let's find our derivative. So with this, we actually have, there's a couple of ways you could do this. We could split this denominator apart, or we could just go ahead and use and kind of simplify those to be 1/3 x to the 3rd plus 1 over x. Or we could just use the quotient rule. I think we could use some practice on the quotient rule, so let's go ahead and do that. So the quotient rule says that we have low d high, so the derivative of the numerator is 4x cubed plus 0, less high, which is x to the 4th plus 3, d low, derivative of the denominator is 3, all over the denominator squared. So if we simplify this, we'll get 12x to the 4th minus 3x to the 4th minus 9 all over 9x squared. So we can combine like terms and get 9x to the 4th minus 9 over 9x squared. We can divide all pieces by 9 and get x to the 4th minus 1 over x squared. All right, so we need to use this derivative to find our critical numbers. So let me erase this. So remember, our domain was x can't be 0. And our derivative is x to the 4th minus 1 over x squared, which can be factored using a difference of squares, to x squared plus 1 times x squared minus 1. And x squared minus 1 is x minus 1, x plus 1, all over x squared. That will just help us to get our critical values. So our critical values are where the derivative is undefined or 0. So it's undefined when x is 0, which we already have in our domain restrictions. So that's not a critical number. It's not part of the original function. So this is where it's where the original function is undefined. It's a value not included in the domain. So f prime of x equals 0. This first factor will never be 0, so it's just going to be these two. So f prime of x equals 0 when x is -1 or 1. And f prime is undefined when x equals 0. This is not a critical number because it wasn't in our domain. Okay, so when we do our derivative number line, we have -1, 0, because that's like an undefined value from the original function. And we do have to analyze what is going on there. So we know that that's going to be from the graph of this, that's going to be let's see, x equals 0. That's a vertical asymptote. Okay, so we know something's happening here. We have like kind of that dead zone on the original graph. So we're going to take some test values. We have 1, 2, 3, 4 intervals, and we're going to plug those into our derivative. All right, so let's plug in like a -2. So if I plug negative 2 into my derivative, this first factor in my derivative is never going to be anything other than a positive number. Because, let's see, we had x squared down there. Okay, because I have something squared, so whether it's negative or positive, that will become positive plus one more. So this part of this is always going to be positive. So I really have to focus on these other pieces. And my denominator will always be positive because something squared. So if I plug negative 2 in, I get negative 2. Negative 2 minus 1 is a negative. Negative 2 plus 1 is another negative. And our first factor is always positive. And then the denominator is always positive. So we'll have a negative times a negative, which is a positive, over a positive. So my first interval has positive outputs. If we plug in a number between 0 and negative 1, like negative 1/2, the first one will always be positive. The denominator is always going to be positive. So we just have to see what happens with those other two factors. So if I plug in a negative 1/2, my first factor is positive, my denominator is positive. Let's see what happens with the other two factors. So a negative 1/2 minus 1 will be negative, and then a negative 1/2 plus 1 is a positive. So with the sign analysis, any number in this interval will give us a negative output. All right, so let's look at a number between 0 and 1. So we'll do f prime of a half. My first factor is positive, my denominator is positive. 1/2 minus 1 is a negative. And then 1/2 plus 1 is a positive. So this goes from negative to negative. So we didn't have a sign change, which means that I'm not going to have a max or a min at 0, which makes sense because that's where our original function was undefined. We have a vertical asymptote there. So now let's evaluate our derivative at a number bigger than 1. So 2 is easy. Our first factor is always positive. Our denominator is always positive. We're just checking out these other two. So 2 minus 1 is positive. 2 plus 1 is positive. So my final interval has positive outputs. Now to analyze what this means. Okay, so I'm increasing from negative infinity to negative 1. Then I'm decreasing. I have that vertical asymptote. And then I'm decreasing more, and then go back to increasing. So what this means, for example, 2, is, let's list out our increasing intervals. We're increasing from negative infinity to negative 1, and from 1 to infinity. We're decreasing from negative infinity. Oh, no, that's wrong. Sorry. From negative 1 to 0. And I'm not including 0 because I have nothing's happening there. I have that vertical asymptote. So I have to do parentheses and then 0 to 1. So if I'm going from increasing to decreasing, that means I'm going to have a relative max at negative 1 something. And then another place I have a sign change is at 1, and that's going from decreasing to increasing. So I have a min, a relative min at 1 something. Now, how do we find the something, what that actual max or min is? We plug our x value into the original function to get our output. So if I plug 1 into that, I will get 1 to the fourth is 1, plus 3 is 4 over negative 3, so negative 4/3. And when I plug 1 in, I get 4/3. So the first derivative test helps us to analyze increasing, decreasing, and tells us where we're going to have maxes and mins, and then we plug them back into the original function to see what those actual outputs are. All right, final example. F of x equals x cubed minus 3x squared plus 3x. So our domain here is all reals. Nothing's going to make this function be undefined. It's a polynomial. Our derivative is 3x squared minus 6x plus 3. So to get our critical values, we want to know where this derivative is equal to 0 and where it is undefined. So again, it's another polynomial, so it's not going to be undefined anywhere. We can factor out a 3x squared minus 2x plus 1. That's a perfect square trinomial. So this will factor into x minus 1 squared, and I want to know where this is equal to 0. So divide by 3, we get x minus 1 squared equals 0. So this will give me square root. I have, if I square root both sides, plus or minus, square root of 0 is just 0. So I get x equals 1. So we just have one critical number. So let's do our line for f prime, and our critical number is 1. All right, so let's see what happens. We're checking, doing a test value between negative infinity to 1, so 0 is an easy one to do, and I'm plugging that into my derivative. So if I plug 0 into the derivative, I would get a positive 3. If I plug a number between 1 and infinity, let's do 1. Nope, we can't use 1. 2. So if I use 2, I'm going to get 3 times 2 squared is 12 minus 12 plus 3. So I get a positive. So what does that mean about this function? So f is increasing and then increasing some more. So this is increasing from negative infinity to infinity, and it is decreasing never. Which means if I don't have a change in sign from positive to negative or negative to positive, there's no relative extrema. All right. Let's go back. The function in example 3 is what we call strictly monotonic. It's either strictly increasing or strictly decreasing. And this illustrates 2 important points. Not every critical number produces a relative max or min. And even though the slope at 1 is 0, the function is always increasing. So I want to show you, if we can look at the graph of this function. Let's just pull that up really quickly. Oh, let's see. Let's cancel that. We don't want to lose all of this. So if we just look at the graph of x cubed, so the graph of x cubed, and the function that we just derivated is a variation of that. So this is just a plain old x cubed, that's its parent function. Do you see how this is always increasing? So this x equals 0 is not going to be a max or a min, but it is somewhere where our derivative equals 0. This is like a turning point. So just because a lot of them will change sign, positive to negative, negative to positive, is not a guarantee. So you do need to check each function to make sure that you actually have a change in sign before you just state that you have a max or a min. All right, that's it for this lesson. We will have a quiz on Friday, just that verifies that you've watched this video. Hope you guys have a great day.